So it's time for chapter 24. We're going to start, of course, with section 1, and we are progressing toward understanding black holes. So we ended last chapter with high mass stars. They collapse because electron degeneracy pressure can no longer withstand the gravity, and the two electrons fuse into a neutron. And so we have the neutron stars, which are super dense. But if the star is large enough, two neutrons that do not want to touch will eventually get pressed together hard enough that they fuse. And in the process, space collapses in on itself and you end up with a black hole. So now, how do we get there from here? Start by asking, what is a black hole? It's a big hole in space and things are sucked up like a vacuum. No, but we'll get there. Okay. So to start with, we're going to talk about general relativity, and gravity and acceleration, and those kinds of things. So let's go all the way back to 1887. Michelson and Morley were two scientists who were trying to prove the existence of the luminiferous ether, the, matter that supposedly was air, and that, light traveling through with it would travel slower than light traveling perpendicular. And so they set up this experiment, and the fact that the experiment had negative results, they could not detect a difference in the speed of light, was the beginning that led through a number of scientists to special relativity with Einstein. So let's look at Charles Schwarzschild. He was a German scientist, and in 1915 he published a mathematical proof that a black hole is possible, and mathematically determined the minimum size of a non-rotating black hole's event horizon. Well, okay, let's start with, he published it in 1915. He'd been working on it for years. Special relativity was published by Einstein, 1905. And this is our normal understanding of space and time, E equals mc squared. So just because I said Einstein does not mean that we have strayed into the realm of, new age particle physics and you're all going to be lost. It really doesn't. Einstein has a reputation for being, exceptionally brilliant and coming up with things that no normal person can understand. That's not true. We have a pretty good understanding of Einstein. All of us will. And then in 1916, he expands on special relativity with the general theory of relativity. So what is that and why do we care? Okay, so there's a couple of things that we need to remember that are absolutes. And these are, the laws of nature. The laws of nature are the same for everyone, everywhere, every when, every time. Every time you throw the ball up, it falls down. If you have ever watched a child between the ages of 1 and 4, they are testing this over and over and over because their brains are beginning to understand that if I throw this ball at the wall, it will bounce back, and it bounces back every single time. So, and the speed of light is the same for everyone. So all of the ideas of relativity follow from these two ideas. So your weight in an elevator. Einstein actually is one of the ones who put forth this idea. This sort of made him think. When you're standing in an elevator, you feel normal. And if the elevator starts to drop, you feel light. You feel like you might be light. If the elevator is moving up, you feel heavy. And, if the elevator breaks, you would experience weightlessness. And so understanding that that is what's going on, is the beginning of understanding relativity. So let's talk about free fall. We have two people and they are playing catch and they're throwing the ball back and forth. And they jump into a bottomless abyss, so they are falling at the same speed, throwing the ball back and forth. For them, there is no gravity and the ball is still moving back and forth. As we look at them from out here, we can see that the ball is going across and across and across, but that it's falling as it moves across. So from their point of reference, there is no gravity. From our point of reference, there is. Point of reference will be very important. So gravity is the same as our experience of acceleration. So we cannot separate them in our minds, really. So we have here a picture of two astronauts that were, basically doing a demonstration, playing with the fruit, showing that the fruit is floating, because everything, including the spacecraft, is floating. It's in free fall. And so what is free fall? We had the picture a minute ago of the people falling, but what is free fall? So free fall is when you are falling, you experience no weight. You do not have any weight. There's no point of reference for you to weigh you by. So if you have no weight during free fall, what happens to light during free fall? So we are falling because we are being pulled by a large gravity source. So let's look at the space shuttle. And so the space shuttle is moving left across the screen and a light is beamed from A towards the front. As the light moves, even as fast as light moves, the space shuttle is falling around the Earth. So spacecraft, to be in orbit, it has to be in a balanced state where it is moving forward and towards the gravitational body at the same speed, so that it is falling constantly toward whatever that gravitational well is, in this case a planet. Well, what you would expect is that light ray stays straight even though the space shuttle moves. But it doesn't. The light ray bends. And so the light ray comes and ends up hitting the nose of the space shuttle, just as if the space shuttle had not bent. So this means that gravity must curve the path of a light, a wave of light, just the same as it curves the path of a mass. This is, science shattering, that light can be bent. So next chapter, or next section, how does gravity warp space? Because is it bending the light or is it warping space? We'll answer that next time.